Okay. All right, guys, let's get started. So today is 350 lab. We're currently in week 4, if I remember correctly. Okay, and today's topic will be hash functions, integrity. I've started grading some of your assignments, so should be seeing those grades by the end of tomorrow, most likely. And then you've submitted one assignment, two assignments. The first one, and then I think substitution cipher, and then the hash XOR is due this week, right? XOR. Okay, and then yeah. Today we're just gonna focus on specific lab. It's an easy lab, I think, honestly. We've looked at the algorithm part last week, right? And today we're kind of focusing on how to use it. So we'll switch back to OpenSSL, which is a really powerful tool. And we'll just do some exercises with it and so on. So we can think about, some applications of hash functions, right? So we use it. So what are some applications, in your opinion, or that you know about for hash functions? We know that's for integrity, but I mean, like, how is it used really? How can you use that idea? Is it just for checking the integrity of a file, or are there other applications of it? You can. Want to know what else hash values are used for? No one? So they're used for malware analysis, for instance, right? So if you think about it, it's what is called static analysis. Basically, we'll see this later in the semester as part of applications. You have a file in your operating system. Think about it. If you take that file and run it through a hash function, you'll get a hash value, right? And that file then, if you ever get that file again, the exact same copy of that file, it should generate the exact same hash. Therefore, think about it. If a file has been flagged as a virus, specifically as is, then an easy way to find that is just to make hash all your files in your operating system, take those hash values and compare them to a database of hashes. If you have a match, boom, you found a computer virus. Does that make sense? Now, there's a way to get around that, right? So if you're a good attacker, then all you have to do is every time you make a copy of the virus, change 1 bit, which is easy, right? Just change the date or something in the file. And when it runs through the hash, it's going to generate a totally new hash value. So it won't be found on the database. Do you see what I'm saying? So it's actually, it kind of shows you how easy it is to build an antivirus scanner, but also how easy it is to escape it, right? So you pay for a decade, maybe you don't do this anymore, but 10 years ago, you would buy McAfee or Symantec, right? And those were just static antivirus scanners. And all they did was they give you a little file with a whole bunch of hashes. That's it. And you were paying money for that. So anyway, obviously today there's a lot of there's like dynamic analysis, which is basically you run the virus in a control environment like a sandbox, and then you look at the behavior of it and try somehow to detect it. But the easiest way, and we'll do that later in the semester, we'll use hash. So I want to do this because I want to stress that, it seems like the less interesting of the cryptography techniques, right? So like symmetric encryption is very interesting. RSA is like fascinating, right? And then integrity and hashes and everything seems kind of boring of it, but it's actually really important. What's another huge application of hash functions and, this idea of creating from a variable length something? It's a big application of it today. Some people speculate in the markets, Bitcoin and blockchain. So all those things are actually based on the principle of calculating hashes, right? So this is another topic we will explore later in the semester towards the end of it. Some of the idea, we'll do it in Python, not in like C or anything, but we'll implement some of the ideas of how, blockchain and Bitcoin and all that comes in and it's based on cryptography, right? It's based on the uniqueness of cryptography, that they're trying to create something unique that can be used as a currency, I suppose, or something similar to that. All right. So I don't know how many of you trade in Bitcoin, but it's certainly a thing. All right. I don't know that there's value in it yet, but who knows, right? So, all right. Anyway, but we'll definitely talk about some applications of these. So it's not just for like confidentiality, although you could say Bitcoin that it's maintaining the integrity of a currency, right? An electronic currency. So there is the integrity component in there, just a different application. All right. Anyway, so those are some applications. So today we're just going to calculate some hashes. So I'll do the same thing I did before. I'll demo, create some text files, and then it should be a very easy lab. Today is almost like a catch-up lab also. Like if you've fallen behind on labs or anything like that, you definitely need to I'll give some time today to kind of help you out on any homework assignments that you have that you're stuck in. All right, so so you guys are seeing Brightspace. I need to turn on the virtual machine, so I'll probably go ahead and do that, and we are recording. Okay. Okay. So let's start. All right, so while it's doing that, oh, before I forget also, so next Tuesday, I plan to attend class, but I may have a family emergency. So if that happens, I will let you guys know, right? And I would provide a video or something like that. But otherwise, currently, I do think right? So, but just FYI. All right, so sorry about that. So yeah, so we have done secret key encryption, Python substitution, Python XOR hash algorithm. So this is, we coded this. I'm pretty sure we got the hash value in the end. And now whatever you got in this code, if you remember, I was trying to make it into hex, and I think I was missing a few functions that I do have in my GitHub. I was looking at the code. It's a little, I didn't add those in. So I will just kind of circle back to that today, to the code we did, and just try to add those functions. But in essence, what I wanted to do was to link that we have the algorithm that we were writing last week. It generated a hash value from a string. Today, we're kind of doing the same, but with OpenSSL, and OpenSSL should give us a hash. And then you should compare that they are very similar, okay? Obviously, these algorithms used in OpenSSL are way more robust than, the one I give you, which was meant to be simple. All right, so we did this. And this assignment is closest on September 15th, okay? So that's like Sunday, I believe. All right, and then hash functions is kind of our lab for today. So I haven't created the link. I'll create it in a second, but basically you can see these are the problems that we're going to do. And there's a PDF that I provided. It's the same thing as in your book, but you don't have to buy the book. You just look at that PDF, which has the commands basically, and that's it. All right, so complete the following 4 problems. As I said, this is an easy lab in my opinion. Calculate hashes for a plain text using MD5, SHA1, SHA256. Then we're going to use something called a keyed HMAC. So calculate hash values using the same algorithms. Then number 3, we're going to corrupt 1 bit. So this is really important, right? Because think about it. You have a whole movie, which has billions of bits. You would hash it, and then you get a hash value. If you just change 1 bit of the whole thing, we do that and regenerate the hash, and you should notice that both hash values are completely different. There should be nothing. And that's kind of part of the definition of hash values. So number 3 is corrupted file, create a file and hash it before and after corrupting 1 bit of the file, report your results. And then now that you know how to calculate hash values with OpenSSL, this part you do on your own, craft an experiment where you would send a file to your classmate with the hash value. So you have to, this problem, remember, relates to integrity. So you have to understand these. If I haven't said this already, you know, I do several practical exams at the end of the semester, which are not written exams. They're like demo exams. So one is the scavenger hunt, where you have, as I said, I think I've explained that I hide something, a message, and you have to understand a lot of tools to find it. The other one I do is the demo one, where I will basically, with your partner, you'll work with them and I'll say, please send this file to your partner, achieve integrity. You see what I'm saying? You need to demo that. So you need to understand. So that's why I insist on these problems in every lab that you're working, because otherwise, if you just do these on your own, I guarantee you, when you get to that point, you're going to get it wrong. You won't know what keys to use. And that's sometimes one of the challenges is just using the things, right? Knowing what is what. All right. So great. So we'll do that. And then, as I said, the fifth thing I'll do today, I may not assign it as homework, but it's just to go over that Python code again that we were doing on Tuesday, I think. We were doing something, right? So just to kind of generate more, you know, more values there. Okay, so let's go ahead and start this. Okay, so let's go back here. So we went over these slides, I'm sure, and this is the same document, basically. Sometimes keep these same problems just for my reference. It's got a little bit more detail. So this is what you're responsible for as far as the homework, right? These four. So let's start, and then the PDF there just has the commands for you. Okay, so I think our virtual machine is probably ready. Yeah. So log in. Okay. All right, so let's create a file. All right, let's start with problem number 1. We're just going to create a file, and I'm going to show you the OpenSSL command to create the hash values, and we're going to interpret that, right? So remember, we're doing variable length to fixed length. So once again, we start up our terminal here. Let's L. Now navigate into the desktop. All right, and I'm going to go into ITS 3050. 2024, there we are. Okay. So substitute XOR, my PRG, we've done that. So these are the two last things that we worked on, XOR hash and my PRG, right? So today I'm going to create a new folder, KDIR. I'm going to call this one Integrity OpenSSL. And you should know what that means. Integrity OpenSSL, we're talking about MD5, SHA1, SHA256. So OpenSSL. All right. So now we can CD into that folder. Right. All right. So we're going to create a file. So I'm going to do nano in my case, plain txt. Okay. All right. And I'm just going to say, put your name there, you know, Mary Smith. And then this is a secret file. Secret file. Another thing I need to show you guys how to do is how to read files. We have to start doing that soon, right? Instead of just hard coding all of our text, we have to start creating little text files because we're going to need to dump keys and things going forward. So remind me today to go over that, please. So it should be pretty straightforward, but I need to provide them. All right, so this is a secret file that will encrypted, hashed. Okay, can do that. And sent to our classmate. It's true. Okay. So we might do, you guys know how to achieve integrity and confidentiality in one shot. Okay. So we should be able to do that and make it a little bit more complex. All right. So should be clear enough, right? So Control X, Y, enter. ls-l, we can see we have our file there. Now, pretty straightforward. We're going to create some hash numbers, and that's it. You know, that checks the integrity. So OpenSSL is the command that we've been exploring. Digest, GST, dash MD5, plain text. That's it. You see that? And it generates a hexadecimal value. So when you, that's the whole process, okay? So we create, and that's what you can send your friend. As you start to automate these things, obviously you would want to dump it into files and use a cron job or something and send things out via email, etc. So that's basically the process. Let's try. So in one of the labs, one of the questions, when I ask you send this to a partner, you would send them the file and the hash, and then they receive it on their end. What do? They grab the same file, hash it, and the two hashes should match, right? If the file has not been corrupted in any way. Does that make sense? Keep in mind, this is why I'm saying it might be important to generate a file and do things like that, because if you're just like copying it from a VM to your email or something, sometimes that process changes characters and things like that, right? And so obviously it's not gonna hash correctly, right? So very important. All right, so let's do another one. So get the hash of the file with 3 different algorithms. So the next example I'm going to explore is SHA1. And then you guys can tell me what your observation is here. So OpenSSL, DGST, dash SHA1, same file, plain dot txt. So what's the difference, basically? The size, right? So the SHA1 is a little bit bigger. Okay, and that, you know, and that's basically the assumptions. The blocks always get bigger, so it's harder for a computer to break them, basically, due to cryptanalytics or a brute force attack, right? Obviously, a brute force attack of all these characters would take, we saw the graphs already, it would take maybe years to perform. However, if you had a quantum computer, in theory, it does things in parallel somehow, right? And so when it does that, it's able to find the answer faster. That's kind of the theory of it. All right. Next one, right? SHA256, and please raise your hand if you're stuck or anything like that. So the next one, OpenSSL, digest dash SHA256. Okay, and then plain dot txt. What do you notice now? Much longer, right? You know, much. So that's the idea. So you can try this, you know, play with it as much as you'd like. All right, so we are going to now repeat the exercise using a flag that's available for these things called the HMAC. And basically, we're going to use what is called a keyed hash. So we're going to provide a key for it. And so once again, here, it's discouraged that you use small keys. So in essence, consider longer ones. Okay. All right, so let's go ahead and repeat the exercise for this. This is actually problem 2. So that was problem 1, pretty easy. Okay. All right, problem 2. OpenSSL. I'm going to repeat. So I'm going to do a clear, I guess. Clear, like that. I only have one file here. There is no bin file that's being generated. Notice, like in the previous examples, instead, we're just printing out the hash. And usually this is, if you've ever wondered, right, you've gone to a software place and you've downloaded a game maybe or something like that, and it said, here's the hash of it. So what they're saying is when you download the file, hash it, compare this to what we provided, and then that means no one has introduced like a computer virus or keylogger or something like that, ransomware, right, into your file. Does that make sense? So I'm sure you've encountered this before. All right, so let's go ahead and do, let's do same example, pretty simple. OpenSSL digest dash MD5 dash HMAC. So you can see here, I'm adding the key. Go ahead and play with these different key sizes. Try different ones, see what happens. I'll just kind of use an analogy here. I'll say like key, secret key, very secret key, very, very secret key. I'm making them longer, basically, and we'll just explore the behavior of it. Okay, so I'm going to do a double quote here. I'm going to say key, just like that. And then the same file, plain txt. Okay, so you can see we have a MAC value there. That's, yeah, correct. Looks about right. Okay, please. You want me to do what? To recreate it? No. Just open the text in it? With Nano? Yeah. So Nano plain txt, enter. It can be any message. It's just something sufficiently long. Doesn't have to be that. Got it? Yeah. All right, great. Perfect. Yeah, so let's do another one here. I'm just going to do up arrow. Okay, so OpenSSL DGST, MD5 HMAC. Now I'm going to do secret key. Notice I'm just changing secret key. And what do you notice about the keys? They're different, right? One ends in C2, the other one ends in B17. Again, this looks more like a hexadecimal notation. Refer back to the ASCII table I provided, and you can take a look for some reference. Let's try another one. So I'm going to do SHA1 now. I'm going to up arrow again. I'm going to do, we've done MD5. Now let's do SHA1. So we're just going to exchange this here. Remember, this is like the modes of operation in a sense, or DES, AES. We're just changing the underlying algorithm, but it's variable length to fixed length. Okay, so SHA1 and then the HMAC. I'm just going to do key here. Plain text, right? So I have it ends 09F. Now I'm going to do secret key. Ends in 32. unlike the previous one, which ended in 9F. All right, let's try another one. Very secret key. I'm just making it a little bit longer. Ensign 61. However, you should notice that the size, the block size, is fixed size. For that algorithm, they're all about the same size, if that makes sense. You can see that. Okay. All right. Pretty easy. So we've done SHA1. Now let's take a look at SHA256. Okay. All right. So again, it's just they're more secure in essence because the block is bigger. It would take longer to brute force, etc. If they could even do that. All right, so OpenSSL DGST dash SHA256 dash HMAC key here. All right, and then I'm going to do plain.txt. So this one much longer because it's SHA256. Right. Let's try. I'm going to up arrow. I'm going to try another key now. So secret key. Same size, but different one. 6B versus 5F in the end. Let's try very secret key. Same size. It ends in FD. So you can see the key important here. Let's try a very. All right, let's just kind of funny key here. This was one of my previous students. All right, so OpenSSL, DGST, HMAC. So I'm doing this with SHA256. Yeah, let's do it with SHA256. So this is going to be very, very long. Secret key. To see if HMAC key matters to within reason. It's a very, very logical brain there. All right, so let's try that one. And as you can see, same size, right? So these are things that you can be aware of with your algorithms as you're playing with them. Does that make sense, guys? Any questions? That's problem 2. Pretty straightforward. Okay. So I don't hear any questions on this one. All right, so we can probably then move on to problem 3, which, if you remember, problem 3 is about changing 1 bit, right? So we're going to change 1 bit, getting the hash of, so here we're going to have to get the hash of a file, minimally changing the file using ghex, okay, which you guys know how to use already. Then observing that the hashes, you know, if we only change 1 bit, they look very different. All right, so I suggest, although I'll do this with a short file, I suggest, as I did in a previous lab, find like 3 paragraphs from Wikipedia or something like that, put them in your file, just something bigger, okay? So that is more convincing of an experiment, but it should be the same results. So just try something like that. So I'm gonna hit clear here, and I'm going to choose SHA256 for this exercise. I'm just going to take my plain 1, and I'm not going to use the HMAC. I'm just going to, you know, so what do we need to do? So I'm going to take OpenSSL, DGST, dash SHA256, And it was, I think, plain.txt, right? Plain.txt. So we generate that, okay, and it ends in 2F E8, right? 2F E8. If I rerun this, 2F E8, that's the whole point. They should match, right? So for instance, you send this plain text file to your friend, your classmate. When they receive it, they will use the same SHA256 to generate the hash. You also in the email have to send this hash value and they should match. Do you guys see that? Can you send that hash value in like it is, or do you have to encrypt that hash value if I'm only asking you to achieve integrity for this exercise? You don't have to do anything, right? So because integrity just means that the file hasn't been corrupted. So I didn't say anything about confidentiality. If I suggest, set in the problem, okay, achieve confidentiality as well, then it's a different kind of an issue. Do you see what I'm saying? Yeah. So I will be changing, not maybe adding a fifth problem. That might be more interesting, but it's the obvious problem, right? I'm going to say a repeat problem 4, but this time achieve both confidentiality and integrity in one shot. Do you guys understand what I mean by that? Right? Okay. So good. So that will be, I'll add that fifth problem because I think it does go here really well. Since you already know how to do confidentiality, you can use OpenSSL, by the way, for the confidentiality part and for the integrity. So you don't need to use code or anything. All right, so let's circle back to problem 3 though. So here we are. We know that if we run that file, it generates the exact same hash, right? So what the problem is asking us to do now is we need to corrupt 1 bit of the file in this case. So you could go in and change a letter and that's equivalent, but we want to be even more specific for when we have cases like, what if you can only change 1 bit of the cipher, right? And because you don't have the plain text file. So you want to be able to do that. So let's go ahead and we should be able to open ghex. And we open the plain file, so plain.txt, okay? And it opens the file in our familiar GUI that we have used before, right? And so we were going to go in here and change something. So I'm going to change this bit, right? I'm going to change that to, let's say, 2, okay? Changed it, right? Change 1 bit. Now you can go ahead, save the file. Whoops. Okay, so that should be changed. You might want to look at it inside, see what happens. So cat plain. What do you guys think happened? You think something changed? Mary, right? The first Y has been changed to parentheses, and we did that by corrupting 1 bit of it. So now, pretty easy. Oops, sorry. Pretty easy. We can do clear here, and we're just gonna repeat. Oh, I shouldn't have gotten rid of the. Yeah. Sorry about that. All right. Anyway, we'll repeat it. So, yeah. So it gave me that, right? So I'll leave that one. I'm gonna go in now. If I run it again, it gives me the exact same thing, right? So I'm just gonna repeat the exercise, add a ghex, change another one, 3, save, close. Okay, run it again. And as you can see, it is now BF instead of the 2. Now, here is where, you kind of have to be do some crypt analytics. Look at those 2 hashes. What do you conclude about them? Are they just a little bit different or are they very different? What would you say? I know it's maybe difficult, but what's your interpretation? Very different, right? Do they have any characters in common or any of the hex values? Yeah, please.
For mine specifically, I see a path of like.
Oh, yeah?
Just not the same.
Okay, all right. Wow. So good eye. Yeah, exactly. So who knows? I don't know how to explain that, but yeah, that's the idea. At least they should be different, and hopefully there are no patterns. But exactly. And you saw I only changed one bit, right? Only one bit changes it quite a bit. Any questions, guys, on problem number 3? No questions. All right. So now the next 2 problems are problems that you guys have to address. So let's go to the bright space. So we are in this module here. Okay. Lab problems. So I think the Word document probably has the more clear write-up. So we've done problem 1, calculate hashes for a plain text, calculate hashes using a key, the HMAC, and then these are the algorithms provided. Those are done. Problem 3 we've done already, corrupt file, create a file and hash it before and after corrupting 1 bit, report your results. So you've seen that it's very different. All right, so the next one is, let's see. Oh, I think I actually did do this write-up, so it is there. So that's what I said. So problem 4, now that you know how to calculate hash values with OpenSSL, what we just covered, craft an experiment where you could send a file to your classmate with the hash value. Your classmate should validate that the integrity of the file has been maintained. You can use email for this task. You must also encrypt the file before transmitting. This last step would provide confidentiality. So I'm saying then, achieve confidentiality and integrity in 1 shot, 1 email. Don't worry about securely sending the symmetric key for this lab, as we have not, we haven't finished that part yet. Does this problem make sense? So here you have to achieve both principles of information assurance, of cryptography, confidentiality, and integrity in 1 shot. That means that you can't send the plain text file, right? But at the same time, your partner needs to be able to read the file, right? So they need to be able to open plain text. So you need to make those choices. Do you see what I'm saying? So how would this work? Who wants to like say it? The process. Who wants to summarize the procedure to achieve this? Anyone? What would you do? You have to do several rounds of encryption, right? Which is how this is going to work from now on. Every time we add a new thing, it's a new round of encryption. Do you want to try? Yeah, please.
Did you start off by encrypting first?
All right, so you tell me. So you take the plain text, right? And you're going to encrypt it. What are you going to use to encrypt it?
Ph.D.
One of the modes of operation, you mean? Like CFD, maybe? Yeah, okay. So OpenSSL, AES, right? ECB, CFD, okay. So you go from plain text, you got a cipher, right? Cipher.bin is the output, correct? Now what do you do? You have to do everything, right? So do you want to try?
You take the hash of it,
Of what?
of the encrypted file.
Of the bin file.
Yeah.
Okay, so then the bin goes into OpenSSL and you generate the hash of it. Okay, great. And then what do you do?
So the encryption in the
Okay, so you're getting.
in the key.
Well, yeah, right now the problem does say don't worry about the secure key. Any key, doesn't matter right now. If you use HMAC and you have 2 keys, that's perfectly fine. Don't worry about that because we need another set of methods to do that part. Okay, but so you have a bin and you have a hash number. So what do?
You send it to the vacancy.
You email it, right? Okay, so then you email the bin and you email the hash, the hash value, and of course the key.
Yeah.
Once they receive it, what do they do?
They, I would say they do the same steps to see if the hash is.
Yeah, but okay, yeah. All right. So what do they, what's the input to OpenSSL here? Do you want to try? No? So on the other end, right? So you receive the file. What do you do now? You take the bin file into OpenSSL with the same hashing algorithm and you generate a hash value. And then what do? You compare that hash value to the received one, right? If it checks out, then the integrity has been achieved, has been met. Then what's the next step? You need to read the message, right? Because it's in one shot. So what do? Decrypt the file, right? You have the bin file, you have the key, you know the algorithm, and you decrypt. Do you guys see that? So this is probably the first time that we've started to combine methods, right? To achieve things. Later, as I said, I'm going to ask you to exchange the key securely. So that's a third method. And then once what about when I ask you for a digital signature? So that's going to be even more. You see what I'm saying? So it's going to get like layers of an onion, right? So, and to achieve different things in one shot. Does this make sense, guys? All right, so this is the problem that you have to do, okay? So I don't really want to demo this part. I would like for you guys to do this part. Please make it clear in your report, right? What you did, you can work with a partner and you just have to do it one way, so you don't have to. You just make sure you do it clearly. And understand it, which is really key because you will have to demo these kinds of things later in the semester. All right, so any questions on these 4 problems for the homework? All clear? All right, so we have a few other things that I wanted to cover today. One of them is just how to generate files. Files from like Python, etc. So we'll do a simple example of that. And that's going to be very important because we've already started to generate keys, right? We generated the initialization vector. And these things are actually binary values, right? So they're byte arrays. So byte arrays being copied into email is a really bad idea, right? And so we're going to instead start dumping these things as files, okay? So we're going to look at various tools such as pickle dump, pickle read, which is something that allows us to take like whatever is in RAM in your computer and just dump it to a file, right? And that can be handy. But we'll start with simple things like just creating simple text files. This shouldn't take that long, okay? So let's go ahead and do that. I'm gonna do clear. So you got your 4 problems. Okay. Just gonna say like basics. Right. All right, so let's start with very basic example. Okay, so let's start with a very basic example of this. I'm gonna do PWD. Say we're in basics. I'm just gonna create a little file here. Read. All right. Files. .p1. Okay, so this is just so that you can start making things a little bit easier by having files where you have your text or you have your cipher, you know, that you'll be exchanging a whole bunch of files. So let's create one, the very basic example. I'm going to do file one. And I'm going to say open. So this is the primitive function of Python to read and write to files. Okay. And then we just have to think about how we can write binary things, which is a little bit more tricky thing to do. Okay, so here I'll just write like normal text to it. So let's do inputs.txt. And then I have several parameters that I can use here, many, in fact, read, okay, write, append, RB, read binary, WB, write binary. Okay, so these are things that are going to be pretty important because everything that we encrypt usually is a binary thing, and that complicates things a little bit. All right, so but let's just start with a very basic one. We're going to let's say write to a file or append maybe. No, append, let's do it. Okay, so now I'm gonna do for I in range, right, colon, and then I'm going to do just 10. So I'm going to write 10 values into the file for some reason. Okay, so then you just, the file, so 1, 2, 3, 4, don't forget the indentation. File 1 is just the handler, the file handler, so it allows you to, you're referencing a file in the system. And then like right now, I'm going to do write. And here I can write several things. So I can do data. And then I'm going to concatenate. I'm going to typecast the int into a string. And then I'm going to add a new line character or enter value. Okay, and these are things just for creating your messages, etc. Okay. So usually always remember to close your files. So file one dot close, open parentheses, close parentheses. It's that simple, really. Okay. So Control X, Y, enter. Clear. So now we are going to run it. So Python 3. Okay, no errors. That's good. ls-l, you can see we have a file input.txt. It does have some data in it. So now I'm going to do cat input.txt. There it is. All right, so it's a simple text file. Any questions? Would you like me to repeat something, show you the code? Raise your hand if you have any issues.
Can I see the input?
Yeah, sure. The file?
Yeah.
The code. There you go. So that's just simple example, right? These are very useful files, as I said. One issue with this class is it quickly starts to have a lot of files involved in the process. Okay, so right, not hearing any questions, let's go ahead and read the file. I'm gonna do that. Okay, now I'm going to read. So the same contents. There's various ways of doing this. So we can try a few. So file one equal open input dot txt, comma. I'm going to change this to R. Just keep in mind, once you start dealing with binary, you have to account for that. And then you can try something like for line in file one dot read lines. So that's one approach. See how that works. All right, so file one dot read lines just returns like a list. So it returns a list of the things that it found in the text file, and then we iterate through it. So 1, 2, 3, 4. So I'm going to print. Basically, I'm going to print line, and then you should always close file one dot close, right? So you can go ahead now. Remember that I did an append here. So this will show you that it will add to that file already. Okay, so let's go ahead and do that. So Control X, Y, enter, clear, Python 3. Bless you. Right, so you can see, there you go. We wrote, and then we read the contents back out. Does that make sense, guys? Any questions? Pretty easy, right? All right, so let's look at other approaches that we might encounter, just so that we're familiar. Yes, definitely. Mm-hmm. All right, so we're going to try something else. This is a library so one of the things that we're going to learn further on in the semester is some libraries that we can use. One of the very powerful libraries is PyCryptoDome. So we're going to try to install it now. And let's think about it a little bit. So PyCryptoDome. I think it's just pip install PyCryptoDome, but we'll have to try it out. Okay. So Control X. So clear. Oh, okay. I'm going to create a new file. I'm just going to call it hello PyCryptoDome. It's just our first library. This will have everything, by the way. So as you start to build much more complex and fully automated crypto applications, it makes sense to have something like this. So let's try it. All right, so basically we need PyCryptoDome should give us the library crypto. And then from it, we can import certain things. So usually we import random because you already know that in cryptography, you want to have random things, right? So from crypto, import random. That. Also for this example, I'm going to I just want to look at the keys so that one of the things I want to show you is public and private keys, what that looks like, and how to read and write them to a file, basically, to kind of motivate why you should start thinking about this. All right, so from crypto dot public, oops, public key, this should be an uppercase K, import RSA. So this is the next topic that we're going to start looking at in the next 2 weeks, right? The RSA algorithm for asymmetric encryption. All right, so I'm just going to leave this here for now. And I'm going to try to run that script just to see if the libraries are available on my computer. They should be, as I have installed it before. Yeah, so it works for me. Do you guys get an error here?
Yep.
Okay, some of you do, some of you don't. Great show of hands if you got this to work. Okay, so yeah, so how? So you guys have new seed VMs, right? Like you've never used it or installed anything? Okay. Did you type Python 3 by any chance? Okay, yeah. And some of you so if you guys that got an error, type Python 3. Does it work for you if you do that?
No.
No? Does it work? You think so? Okay, so how about over here? Does it work? Well, you're supposed to get exactly what I'm getting. Okay, so if you get this behavior, then that means it worked. So everyone got it to work? Okay, great. All right, so perfect. So yours doesn't work?
Yeah.
Are you using the seed VM?
Yeah. Saying
Okay, how about, because it's strange, right? Because you have a new seed VM, just like some other people who have a new seed VM and it works for them. So let's take a look at the code. Did you make it uppercase C maybe? Can you check that all of this matches? It should be an uppercase C. Guys. If you get this library running, then that's a really good thing. So that's what I'm trying to make sure right now. Still? Okay, so now it works? Yeah, I figured. So it's something, if you're getting an issue, if you're using the seed VM and it's brand new, that's one of the advantages of using the seed VM is that all the libraries are there. So, okay, so it seems like everyone has it, okay? All right, so perfect. So the last thing I'm doing is just kind of showing you this idea of the files, motivating. So let's generate some keys. So this is going to be your first key generation, right? And saving it to file, okay? All right, so we're not necessarily using those in this lab, but it's just something I want to cover. All right, so given that this is one of the easiest labs we have. All right, so we're going to generate a key. So to do that, I'm going to use RSA. So now I don't have to create like a random sequence of bits and convert it to byte array. Instead, I'm just like using a library to do that for me more effectively. Now, I should say, although this library is very solid, in my opinion, it's still only probably for academic purposes. You shouldn't be using this to encrypt things. If you have a need, then use OpenSSL, which is a much more robust program for that. That's for Linux, right? So it's made for users of Linux to trust it more. This is code, and so you never know if it's got a bug. All right, so let's go ahead and generate the key. So you're going to do generate, and then you'll see what I was saying about writing binary, right? WB and RB and so on. All right, so key equal RSA dot generate, and you specify a size, right? So it's 2048, right? So as you can see, you can specify the size of the keys. That's really important. Keep in mind, the bigger they are, the more impact it'll have on your performance of the encryption. Okay, so once that's done, let's just run the code line by line and make sure it works. See, it took a minute there. You see that? Yeah, so there we go. So the code is running. Okay, now let's go ahead and once we have this generates the keys, and the public key is basically in key. So it's basically both keys are here actually. So like me using this, maybe it should be keys instead. It's maybe a little confusing, but both keys should be there. So what we need to do is extract them, right? Public and private. We'll look at the theory of all of this and how it works. Don't worry about it in a lot of detail. We'll look at the math background for this. But for right now, I'm just using the library. I'm going to generate two keys and write them out to file, and then you can have them. All right, so I'm going to do private key. Okay. So it's going to be key dot export key. So export underscore key like that. Okay. And then I'm going to just write the private key and the public key to a file. So let's do the first one. File out. The file out. Open private dot pem. Oops, sorry. Private dot pem. The extension doesn't really matter here, but I want to be consistent given that in general, you call these PEM files and OpenSSL will automatically generate them with these extensions. So as we will see later on. But these should work. I mean, these are like very solid exported keys. So open private dot pem, and then notice here what I'm going to do, WB. Do you see that? So that means write binary because yes, the keys are now binary. If you were reading them, you'll have to do RB and things like that. All right, so I've created the file, and then I am just going to write it, and because it's binary, I can just dump it as a binary array basically. So I'm going to say file out dot write, and I'm going to write the private key like that. Okay, and then I'm just going to make sure I close my file. So file underscore out dot close. Make sense? Okay. Then I'm going to repeat the exercise for the public key. So I'm just going to say public key. And I'm going to say key dot public. This should be all lowercase. Public key. And then dot export key. Right? So from the keys, extracting the public key and then exporting it. And then after that, it should be the same process. File out open public key. So notice the name changes here. This would be the public key. public.pem, basically. And then notice that we use WB, okay, WB for write binary, and then now file out dot write. Okay, and then we write public underscore key here, and then make sure you close the file. And that should be it. File out dot close. And as I said, I'm illustrating the use of reading and writing files because you're going to have to start doing it. Okay, when you're not using OpenSSL, OpenSSL currently conveniently, right, will generate the keys in a file format. You've seen that it generates a bin file, given a text file, and so on. But the code, you have to do all that on your. All right, so let's go ahead and hit Control X, Y, Enter. Hopefully this will work. So let's hit Python. So let's do, yeah, let's do Python. Okay, no errors, that's good. Does take a little bit of time. I don't know if you saw that lagging effect there a little bit. So now let's do ls-l. Okay, we got some files in there. As usual, you want to pay attention to the parameters of the files. So this is your private and your public, right? In terms of size, do you notice something? You have any observations in terms of the size of the output? Yes. Private is larger than public. Yes, this is how the algorithm works. Usually the public key is shorter than the private key. Private key is what you're going to keep as a secret, so it makes sense that it's the more, it needs to have more complexity and so on. And that's just how RSA works. This is literally the algorithm that we have available. So the way that I do this is we're going to look at the code. You will write RSA from scratch. Like literally you'll see all the components. And then we're going to use PyCryptoDome as the library, a more robust representation of it. Okay, but it's all pretty consistent. We'll get to that, but there's plenty of time for that. All right, so now let's take a look at the files, right? So we want to look at them. So I'm going to do cat of public. Cat of public.m. There it is. If you notice, looks like hexadecimal values of some kind, right? So that's your public key. It literally, the PEM file uses this format, right? You know, if you've ever used SSL or sorry, SSH, this is the format of your public and private key files. If you've ever used configuration of HTTPS, this is the format. So this is the actually like the common format that, and that's what, you know, the extension is a .pem file. Any questions here? So we generated the public key. Now let's take a look at the private key. And you can see a little bit longer, right? But that's going to be your file again. So I wanted to show this exercise because, you know, it's not practical to start copy pasting, you know, and sharing these files. So you have to get into the habit of, you know, writing out your information to files, either your ciphers or whatever it is, as we start moving. Because OpenSSL does it, but not anything else. All right, so I think this is good. This was clear enough. You guys now are masters at reading and writing files, so we can you know assume you guys know how to do that. All right, so and then I think there's one more thing I want to do today. I just want to look at something. In the time that we have remaining, go ahead and work on that last problem. So I'm going to go back to, and if you have questions, definitely ask them. Remember, next week, I'm going to move on to something else, right? Which is going to be drilling down on modes of operation. We're going to go back to XOR and implementing now one of the modes of operation, such as ECB and CFD, for instance. So that will be the focus of next week. And then after that, RSA, most likely. So the problem that you are responsible for that I don't really wanted to use, solve this one. So solve number 4, right? So use OpenSSL, achieve integrity and confidentiality in one shot as we described, and work with a classmate, okay? Right, so yeah, so use the rest of the time for this, or if you have any questions, go ahead and ask. I'm going to pause the video here, given that I don't have any. Okay, so I think I can. Stopping.